Okay. So we're going to be talking today about some material that builds a little bit on the ideas advanced last time, and then as time allows, going on to a different topic that I'm going to be asking you to include within your ID5 submission, which is an estimate, a formal estimate of the total number of defects, and by extension, the number of undiagnosed defects that have not yet been discovered within your systems. Okay, so we're going to be talking about a methodology for estimating that. But the first lecture is on capturing commonality within programs via interfaces and classes. And this builds on our discussion in the past few lectures of techniques that object-oriented programming offers us for abstraction, for capturing sets of state and methods associated with objects. We've talked about the use of subtyping. We've talked about the use of subclassing. And today we'll see an alternative in the form of what are called mixins on the one hand, where you can have essentially many of the benefits of subclassing without needing to worry about the Liskov substitution principle, without needing to worry about the subtyping issues. There's no subtyping involved. You simply mix in functionality, mix in implementation into your class in a flexible way. Secondly, I'm going to be talking about the use of what are called skeletal implementations, which is a technique you see a fair bit in the Java libraries, the Java standard libraries, in which is being used by jar files, libraries that you can get from third parties. And you want to be able to understand some of the benefits it offers and why it can form an effective alternative to, and flexible alternative to classic simple subclassing. Okay. So we're going to be talking about use of skeletal implementations before going on to a discussion of defects as time allows. That may have to wait until next time. Okay, so if we're considering object-oriented programming languages like Java, like C#, I could trot out a number of others, they provide a variety of mechanisms for capturing, for bundling together state and so properties and changing characteristics of an object with methods of an object through defining constructs such as classes and such as interfaces. So an interface in a language like Java, or an interface language like C#, or a language like C++, or Objective-C, these interfaces define contracts. They define a set of promises that need to be adhered to in the form of methods, what they require as far as parameters, what they can return, what they can signal as far as exceptions. And it provides no implementation, right? You declare an interface like the collection interface or like the set interface, and you have no implementation provided with it. You simply have a set of methods that you need to implement in order to be considered having implemented that interface. You need to implement these characteristics to be viewed as a collection, for example. And I've highlighted the past few lectures that those contracts are not merely about textually providing those methods, satisfying those methods. You need to have those methods' behavior be consistent with what's promised in this interface. But I'm not going to be dwelling on that part of it today. Fundamentally, we have interfaces and then we have classes. And classes are different than interfaces. They do provide an interface of sorts. They provide a contract, but they also provide an implementation of that contract. They provide mechanisms to implement the contract. Instead of just promising the what as associated with interfaces, what is done. they provide a whole how it's actually accomplished. Okay, and you folks, I'm sure, have made use of abstract classes before. How many people in here have made use of an abstract class? What's the difference between an abstract class and a concrete class, a non-abstract class? What's different, roughly?
Abstract class doesn't contain a full implementation.
Yeah, it doesn't contain a full implementation. It leaves some pieces as not yet specified. So in a certain way, you could kind of think of it as a little bit of an interface, a little bit of a class. There are certain things that are not provided for implementation, and many other things which are provided. Now, when we think about interface implementation or class-based inheritance, there's a set of trade-offs between them. Why would someone use an interface as opposed to use inheritance, as opposed to using a class and then subclassing from the class? Can anyone mention to me, I'll put that up there again in a second, but can anyone mention to me some of the trade-offs? Like, why would you prefer a class, for example? Why if you want to declare a set of mechanisms, why might you put that into a class rather than into an interface? Anyone?
I mean, if you're going to redefine the subtypes, you get to reuse your code.
Okay, yeah. So you get to reuse the implementation. You get to reuse the how. You get to reuse the code that someone created, and the fields and so on that accompany that, which actually get the work done, right? So that's something that's often wanted, right? You get to be able to reuse that hard work that went into it. Ladies and gentlemen, why might you prefer an interface? What are some things you could do with an interface you can't do with a class?
You can extend multiple interfaces.
Good. You can extend multiple interfaces. Excellent. So you could have a given object that's both serializable and it's iterable and it's serial numbered, what have you. Okay? So interfaces are more flexible. They can capture non-hierarchical relationships. They can capture relationships like this, where an equilateral triangle might be both a regular polygon and a general shape, for example, right? And that affords us some extra flexibility. Lets us mix and match sort of characteristics with respect to our classes of interest. On the disadvantage side, there's no implementation provided. It's just a specification of the interface. Class-based inheritance has the advantage of reusing implementation, but you have to be very careful about the scope substitution principle in terms of reusing it. And you can get situations where you distort the inheritance hierarchy because you can't inherit from multiple things at once, and you end up kind of force-fitting a lot of functionality into one class. Okay, things from two conceptually different areas. It turns out multiple inheritance is dangerous. Okay, so if we had, if we want to have sort of a taxonomy that isn't broken down just in a totally hierarchical way, but we want to say that a given animal, say a dog, has several different roles that it provides, and we want to have, say, an interface associated with each of these roles, we might do that with interfaces, because now a dog could implement the provide companionship, the race, and the entertain interface. A little bit of a fanciful example, but the point is sometimes we have particular classes and we want them to play different roles, and we want to be able to mix and match our classes with the roles. And we can do that through interfaces, right? Are people comfortable with that? We could say this cat class implements this interface and this interface. The dog implements these three interfaces, right? Make sense? Okay. So we could have something along these lines, right? Okay, so there's if we want to capture this through inheritance, we could do so in a couple of different ways. For example, we might want to have a research assistant, and that's simultaneously a student and an employee. And there's several different ways to do that. We could, for example, define something that's a student employee, and then have research assistant derived from that, in which case we've kind of linearized something that we want. We want naturally to have two separate lines, but we could linearize it into a single line by having employees, student employees, or research assistant, or have students at the top, student employees below that, and then research assistant. It's not too comfortable. A classic way of trying to deal with this in object-oriented programming has been multiple inheritance. How many people here have used multiple inheritance before? Okay. Oh, okay, a couple. So give me a language which supports multiple inheritance.
C++.
C++ supports multiple inheritance. And there's a variety of other languages which have attempted since the 1970s to support it. This can provide some easy ways of trying to deal with a situation like this. The issue is that there are some confusing components of this. And in C++, you actually see this, no pun intended, quite significantly. So if you're using multiple inheritance with C++, there's some classic problems that can come up. One problem is that the most classic problem is what's called the diamond problem. Okay, so here we have a single class that has multiple parent classes, but those have a common class from which they derive. So employee is a person, a student is a person, and a research assistant is both a student and employee. And there's several questions that come up in this context. One is, is the person from whom employees derive, the student derive, is it supposed to be the same person, or are those two different persons associated with it? In this case, it's clearly the same. But there may be cases where you derive from two superclasses. You don't want them to share that super class, for example, that ancestor class. Okay. Another issue is when you call a given method on research assistant that's implemented by person. Suppose employee defines it and student overrides it. Both of these override this method. Which one do you call? Do you call the one in student, or do you call the one in employee? That's not so obvious. And in C++, you can actually enforce the structure, or you can have them do it separately. Does anyone know how you do this in C++? How do you force it to use a common class? Well, you can have a virtual base class, and you can force it to have only essentially one copy of that. But it gets quite messy. It turns out there's some other dangerous things about it in C++ where, if you pass this guy, research assistant, as a student, or you pass it as an employee, it might only be partial information that's passed. It's not information about the whole object, and it can get confusing. So multiple inheritance, without going into a detail, it has a set of challenges associated with it, okay? And it should be used cautiously. Even when you have support in it, like Objective-C or Java, it should be used with caution, okay? There's confusing things because of it. A more flexible mechanism than multiple inheritance has been proposed, again, since the 1970s. And in recent years, it's really gotten a lot of extra backing behind it. I'd say it's probably now more popular than multiple inheritance. Multiple inheritance, it's long been known to suffer from this so-called diamond problem, to suffer from this issue of which one do you call. And with Mixins, there's a clearer conceptual model. So Scala as a language, which was a really up-and-coming popular language, which is increasingly being used. Very nice language for anyone seeking to learn a new language. I'd recommend that. But also by Ruby, Python, and some older languages as well. So mixins go by various names. In Scala, you'll find them under the name of traits. Okay? They're not always called mixins. That was the original name used in CLOS, in Common Lisp Operating System, Common Lisp Object System back in the 1970s. So mixins seek to avoid this sort of trade-off between flexibility, like we get with interfaces, and reuse, but providing small units of functionality. Okay, they provide bits of implementation. Let me say that again. They provide bits of implementation that you can mix in with your class without making promises like you do with Liskov substitution principle, without needing to adhere to the promises. So here you can mix in implementation without needing to worry about the Liskov substitution principle. Okay? So the idea is that there are these little bits, these little nuggets, these little chunks that you're going to mix in with your class to provide certain types of functionality. And you'll build your class up with one or more of these, potentially, if you want to make use of them. And those will add little bits of functionality to your class. But your class isn't making promises in accordance with these items in a subtyping sense. Okay. So there's often no subtyping assumed with this. Okay. So we're going to see some examples here in just a second. But mixins in the form of traits are a notable feature with Scala and are increasingly supported. So a variety of ways of implementing mixins if the language doesn't have recourse to them. I want to give you a flavor of how they work. Okay. So this is an example in Java which currently doesn't work with Java. Okay. This is a kind of pseudo example because you folks know Java. I thought I'd use it. But it gives a sense of how these things work. And I wouldn't be surprised if Java 9 ends up supporting something like that. How many people here have used generics in Java? Syntax like this. Okay, a lot of people. Good. So here we have some Java. Good. And you'll notice here that we have two classes which are conceptually mix-in classes. Okay. So here we have a timestamp class, and here we have a serial number class. The idea is that we'd like to be able to weave in, we'd like to be able to introduce this functionality for being time-stamped into an arbitrary class. So if we have a class, maybe it's a class for a hash table, or maybe it's and we want a timestamp associated with the last time we updated the hash table. Maybe the class is for a person, and we want the timestamp where they were born, or whatever. Here we have timestamp class, and the idea is we're going to be able to say something like timestamped of some class, and using these generic as a type parameter. So timestamp string, for example. And that would give us a class which now has this ability to store timestamps. So we can basically, as soon as it's created, it remembers when it was created, and then it's not shown here, but we could ask it what its timestamp is. So it records when it was created with it. Okay. So we could have a timestamp string, for example, and that would be a string. It has all the features of string, but it's timestamped. It has this extra little bit of functionality with it. Or we could have a serial number class. Again, it takes the class as an argument, takes the class as a type parameter, and it extends that class, actually. So it's actually implemented with inheritance. And here we're keeping track of a serial number for this thing. So every time we create a new one, we increment some counter, and this is something which is maintained statically. So every one of these, every instance of these things gets a different serial number. Okay. Okay, so we could then have a serial number timestamp string, for example. We can mix in the functionality from this guy with the functionality from that guy. In other words, the serial number, we can have atop the timestamp and have a class that has all the features of string, but both these sort of features. So we've woven in some of this implementation into our class. Let's take another look at, well, this is it in C++, which actually does work. C++ has a more flexible template mechanism than does Java. Java actually doesn't allow you to do this extends T. That's not compatible with how Java implements generics. C++ has a more general mechanism, and you can, in fact, inherit from a T here. So we can actually have that. So mixins are a way of introducing this functionality, introducing implementation, adding some methods, adding some fields, the actual implementations of those, so you can have extra abilities in your class. Okay. Let's talk about another way of doing this, achieving many of the same benefits in a language like Java. And this is this use of skeletal implementations. And you'll see these a lot in Java libraries these days. You folks may have used these. And we'll get a bit of a flavor as to why, the motivations here. So the idea here is that skeletal implementations provide most of the advantages of inheritance without loss of flexibility. You're not limited, for example, because you inherit from class A, now you can't inherit from other classes. We use interfaces to describe functionality, and then we provide an abstract class that implements the interface. It leaves certain methods to be filled in, but it provides other methods, other non-primitive methods, okay? And then, if people want to use the interface, they can implement the interface, but they can use your skeletal implementation to make it extra easy. Okay, so let's take a look at this. Okay, okay. So here's an example skeletal implementation class. So here we have this abstract map entry. It implements an interface, map.entry. Okay, and it gives a bunch of methods here, but it leaves these methods unspecified. In other words, this is an abstract class, and therefore it doesn't define these methods. Who's going to define these methods? Can you tell me? Who's responsible for defining these methods in red?
The subclass.
Yeah, subclass. So we're going to need to, we can't use this class, we can't create an abstract map entry directly. What we have to do is we have to subclass it. And we have to do subclass in a way that defines these two methods. Right? So we're going to be filling in these two methods. So let's take a look at that. So for example, we might have a, this is one example of using this. We might have a bit of code which creates a new abstract, here it would be abstract map entry, or abstract list would be another example of this. And you'll notice what it's doing here. Can anyone tell me what this is doing? Someone who's comfortable with the Java syntax? What's going on here? Return new abstract list, begin curly and end curly later. What's going on there? What's happening in this code?
An anonymous class?
It is an anonymous class. So we're creating an anonymous class, and what are these methods here, like object get, int size, object set? What's going on there? Why are there suddenly methods inside our code? Why do we have methods appearing in the middle of our code here? After all, we have some code. This is inside a method called intArrayAsList. Why are we suddenly having internal methods there? Anyone know the syntax? We're creating an anonymous class, and what are these methods? They're the methods of the anonymous class. Thank you. I'm not asking for anything special here. These are the methods of the anonymous class. We're filling in these methods. And guess what, folks? If we did that with this case, which would those methods be that we'd be filling in? It'd be these ones that we didn't specify. So these are probably the methods that were left unspecified by abstract list. These are the ones that we need to define in order to create an abstract list. Abstract list probably defines a whole lot of other methods, but we have to fill in these critical ones to complete the picture. These are just the ones that we need to finish the job. Okay, and you'll notice, and it's quite interesting, that, for example, these methods here are referring to A. Where's A defined? Is A a field of abstract list? Where's A? Huh? Where's A?
In the parameters.
It's up here. Yeah, it's up in the parameters here, folks. So we've actually passed in A. Now we've created an abstract list that refers to that A. It sort of remembers that A and refers out to it. And this is manipulating. This abstract list is manipulating our array as part of it. Okay. So we can actually refer to things that are in the surrounding environment here, to objects in the surrounding environment. So here we're filling in these key pieces. If we were working with this class on the previous slide, we'd be filling in these key pieces when we created a new abstract map entry. Does that make sense? Yeah? So just like we're filling in these three methods, if we were to do in our code new abstract map entry, we'd be filling in these two methods typically. Right? People comfortable with that? Okay. Now, another way to use these things, if we had abstract map entry or abstract list as we're doing it here, we could do something like this. I have class, X list, and we fill in these extra methods there, right? We don't have to do it like this in the middle of code. We could actually define a class which extends it. The problem is, ladies and gentlemen, that, so this is fine. It's just that sometimes this doesn't cut it, because you want to actually inherit, you want X list to inherit from something else as well. Maybe you want it to inherit from some other superclass you created. And now because you've extended abstract list, you're not able to do that. So how can we do that? How can we deal with that? Well, one way is you could say, hey, look, this is a little bit subtle, so pay attention. So here we have X list. We could just implement abstract list, but maybe we want it to actually extend another class. We want it to, just like we sometimes seem to want multiple inheritance, conceptually we might want our X list here to conceptually inherit from Y and inherit from this abstract list, right? But we can't do that with multiple inheritance in Java. It doesn't allow it. And it doesn't allow it for us for our own good. Okay, multiple inheritance is responsible for a lot of bugs out there in cases where it is used. You have to be very careful with it. And Java tends, in its normal style, to be sort of more cautious about enabling that. It tends to be simpler in what it enables. So suppose we wanted X list to get all the goodies that are in this superclass Y and all the goodies defined in our abstract list. We can't just say extends Y and abstract list. So what do we do here instead? Well, we say X list extends Y, but it implements list. What is list here? This is it says implements it, it's interface, yeah. And then in the actual code for this, ladies and gentlemen, we just create a wrapper class. Remember we saw the wrapper classes last time? All it does is delegate. You have to define all these methods, but it's trivial to define them because you just delegate. You just say, oh, you want my size? Hey, buddy, tell me your size. You just say that to each of your delegates here, right? So here, what's our delegate? Well, we just create a new abstract list, we define these methods, and then we've got our delegate, and we can just ask it every method that's asked for us to do, that for abstract list, we just pass it on to this delegate. So here, ladies and gentlemen, we get the benefit as if we're inheriting from both Y and abstract list in terms of not having to write a lot of code, but we have to write these wrapper methods, and each of them will just delegate. Each of the wrapper methods for abstract list will just or for list interface will just delegate to list delegate. So, you know, in many cases we may be able to do this. If we can't and we want to inherit from something else, we still don't have to write all the code associated with implementing list. We could just get a delegate here by implementing the couple pieces remaining in abstract list and just delegate to that. Does that make sense? Are people comfortable with that? So we've implemented the list interface without having to go and build up our own implementation from the scratch. We've been able to build atop this abstract list implementation. Are people comfortable with that? It's called a skeletal implementation. Are you okay with that? I ask because during the final exam, it's evident that students are sometimes not okay with that. Okay? I know time is going to pass. Let's see how these can be used to accomplish mixin type functionality. So here we have an interface timestamp. And that interface has a single method, get timestamp. Okay? We're going to have another interface, iSerial number. And that's going to have something which returns a serial number. Okay? Now we could have an abstract class, abstract timestamp, that implements the timestamp, iTimestamp interface. We have an abstract class, abstract serial number, that implements iSerial number. And then we have a timestamped serial number string, which extends string. It implements iTimestamped and iSerial number. Where have we seen this type of thing before, where you extend one class and then implement two interfaces? We saw it there, right? We extend one class, because that's all that Java allows, and we implement interfaces. And that's what's going to happen here. Okay, so we're going to have a string, we're going to extend a string, and we want to extend it so it has these nice type of goodies with it. That it knows how to keep track of a timestamp. It knows how to keep track of serial number. So what? I thought I corrected that. Pardon me. There's a missing plus there. So here we have this class. It's going to be a timestamped and serial numbered string. We're extending string, we're implementing those, and how do we implement those? We implement them through abstract classes. So here we have our implementation of timestamp, and we just create an abstract, a new instance of this abstract class. And there's nothing to fill in this case. They're particularly simple classes. And then when we call get timestamp, we just return the appropriate timestamp. We just delegate in the appropriate way. So this is basically the same strategy as we used here, where we simply delegate. We create an instance of this abstract class, and then we delegate to it. Here we had to fill in these pieces. Here there were no pieces to fill in, so we could just delegate to them directly after creating it. And we basically implemented a timestamped and serial numbered string by reusing these mechanisms here. We didn't have to go and define get stamp. We didn't have to go and define this get serial number. We could just, in our own way, we could just delegate to these. Okay? Does that make sense? Yeah? Okay. So what are the advantages of doing these sort of skeletal implementations in a Mixin type of fashion? Well, you can escape from the single parent constraint of single inheritance. You can essentially handle arbitrary mixins. I mean, here I did it with two, but I could do it with several others as well. And for each of them, yeah, I have to go through the ritual of kind of delegating, but I don't have to implement it from scratch. I don't have to create all my own data structures. I just create one of these abstract classes, maybe filling things in the meantime, and then I can delegate to it. And I have polymorphism here, folks. Guess what? I can pass this guy around as if it's an iTimestamped or serial numbered as well. That's kind of nice. And I can reuse code. In this case, it's trivial, the code here, but in general, it could be quite complex. Like our code here, there could be a lot of code we don't have to implement. Someone else has implemented, someone else has tested it, and we can reuse it. Does that make sense? Yeah? Okay. The disadvantages are, well, we have to write this delegation code, the wrapper code. And just to be clear, that's sort of wrapper code. And there is an explicit class required to capture abstraction compared to being able to do something like this, where we could just simply compose them together. Okay. And I should note that some other languages like C# provide other ways of accomplishing these things, like extension methods, which can add methods in a way to classes that already exist. Okay. Anyway, so what we've seen here is ways of capturing commonality with interfaces and classes. We've seen the use of these. We've seen this notion of a mixin, which is growing in importance. And if you folks become professional software engineers, there's an excellent chance within 5 years you may be using these. So it's important to understand this notion of a mixin, that you could kind of put together these bits of functionality, such as traits in Scala. We've seen ways of trying to implement them. We've seen skeletal implementations, which provide one way of kind of mixing together a set of functionality in a way that approximates multiple inheritance, can allow us to effectively extend multiple classes, but we have to provide a little bit more mechanism in terms of delegation. Okay? So I do expect your folks to remember some of this, and skeleton classes, wrapper classes, I expect you to be comfortable with. So if I ask about wrapper classes or skeletal implementation classes, if I ask you to interpret what's going on here on a final exam, I will expect you to be comfortable. You can tell me what's going on. Is that okay? Any questions before we have a whirlwind cover of defect estimation for your application within the next week or so? Nothing? Okay, so let's stop that.